Welcome back. Now we will discuss the basic use of arrays in MATLAB. This is closely based on Chapter 3 of the excellent MATLAB book by Gillot, which I think you should get if you don't already own. The presentation deals with arrays. Array is a collection of multiple numbers, either in a list or a table. The list, if it's a list, it could be in a row or a column. The concept of an array is just, at least when I use the word array, I'm talking about a storage device in a computer designed, a conceptual device in a computer designed to hold numbers. That's what an array is. It just holds a list of numbers or a column or row numbers or a table of numbers. It doesn't specifically have the rules of matrix algebra associated with it, but for that I'll use the word matrix. But here today we're talking about both arrays and matrices. So the mathematical rules of dealing with matrices, the mathematical rules of dealing with element by element mathematics, which might be called array math or just ordinary math. So we'll talk about both of those, and random numbers. All right, so an array is a rectangular arrangement of numbers with one or more dimensions. A vector is not specifically the science vector. In fact, it has really little to do with the science vector you learned in physics. It is more the mathematician type of vector, which simply means a list of numbers, or could be other things, but mostly numbers when you're dealing with MATLAB. A scalar is a specific term for an array with exactly one row and one column, a single number. Technically in MATLAB, everything's an array, so even a single number is like an array with one row and one column. A matrix is specifically an array that is subject to the rules of linear algebra. Now, some people use the word array and matrix interchangeably. I kind of find that a little confusing. I try to avoid that use because matrix usually to most people means that it follows the rules of linear algebra, whereas array to most people, it may or may not follow the rules of linear algebra. It's mostly just holding a holder place for numbers. So as far as some math operations, use the plus sign to add two arrays or add a scalar to an array. Works pretty much the same whether you're dealing with matrices or regular arrays. It's going to work element by element. Use the minus sign to subtract a scalar from an array. The thing to keep in mind, if you're using a scalar and an array, that scalar will be added or subtracted from every element of the array. So if you do an array minus a number, that number will be subtracted from every element in the array. But if you have two arrays, then the only way you can do addition or subtraction is if they have the exact same size and shape. So keep that in mind. You can't add, say, a list of numbers to a table of numbers. That doesn't mean anything, regardless of what type of, whether you're doing array mathematics or matrix mathematics. When adding A and B, MATLAB adds corresponding elements. So it adds the element of the first row and first column of A to the element of the first row and first column of B, and so on. Top left number in A gets added to the top left number in B, and so on all the way through the array. It's just a bunch of additions. It doesn't require a loop. Some people, when they first start messing with MATLAB, they think they have to write loops around things because that's how it's often done in regular programming languages. But MATLAB just does it all automatically. If you say A plus B, it knows that's a bunch of additions and just does them all without any loops. It basically puts the loops in there for you. And then it adds the first row and second column of A, the first row, second column of B, and etc. So element by element it adds. It's called element-wise addition. That's really all there is. Whether you're doing matrices or arrays, it's the same rule. When subtracting two arrays, A and B, MATLAB performs an element-wise subtraction. In general, an operation between two arrays that works on corresponding elements is called element-wise operation, or I'll often just call that array mathematics as opposed to matrix mathematics. But element-wise is a good way of understanding the term. Each gets matched with the corresponding pair in the other array. You might think that's the normal way to do things, but if you're used to working with matrices, element-wise often is a little unusual, especially when it comes to multiplication, which we'll get to in just a second. Here's an example you can see on the screen where the corresponding elements of A and B are matched up in the addition and in the subtraction. A11 represents the value in the first row, first column. A23 is second row, third column. It's the row number followed by the column number. That's the way things are usually done with subscripts. That's not A23, that's A23, second row, third column. And you can see how it gets added to B23 in the addition problem, but in the subtraction problem, it's A23 minus B23. So that's the way, element by element, it's going to do the math. Now, when adding a scalar to an array, MATLAB adds the scalar to every element of the arrays. And when subtracting a scalar from an array, it's going to subtract that scalar from every element. So it automatically kind of like expands the scalar, so it's the exact same size and shape as the array you're putting it with, makes a whole bunch of copies of that scalar, adds them or subtracts them from every element of the array. So for instance here, where you see that I have a plus c, where little c represents just a single number, a single scalar, instead of that being an error, what MATLAB automatically does is it adds c to every one of the 6 numbers in A. And then if you subtract a single number from A, it's going to expand c, so there's 6 of them, and it's going to subtract it from every one of the elements in A, if you do A minus c. When adding a scalar to an array, MATLAB adds a scalar, I think. Yeah, that's what I just did, sorry. There are 2 ways of multiplying matrices, matrix multiplication and element-wise multiplication. This is probably the more confusing part. Everything up to now has been pretty much the same, whether you're doing element-wise mathematics, what I would call array mathematics, or if you're doing actual matrix mathematics, which follows the rules of linear algebra. Matrix multiplication uses the rules in linear algebra. That's the standard way of doing things in MATLAB. MATLAB, you might think the word mat stands for matrices. It means it's going to do the rules of linear algebra. That's built into the tables of numbers. Unlike regular programming languages where you have to teach it to do matrices special, you don't have to do anything special for that in MATLAB. MATLAB automatically assumes you want to treat everything using the rules of linear algebra, which is awesome and it's convenient. It's done with a simple asterisk, which you might expect for multiplication. So A star B is going to be A times B, but it'll only work if A and B are paired up properly according to the rules of linear algebra. The rules of linear algebra require, therefore, that the number of columns in the left matrix, the first matrix, has to equal the number of rows in the second matrix, so that they get, it's row times column, kind of like a dot product. The elements of the row of the first get multiplied by the elements of the column in the second. Item by item, they have to multiply out, and then those multiplications, those individual multiplications, are added up to create a single number in the resultant of the multiplication. That's the normal. And then here's an image to show a matrix problem that you might use this for. One of the most common problems in linear algebra is simply n equations and n unknowns. This graphic shows 3 equations and 3 unknowns. The a's represent the coefficients. The b's represent the constants in the equation. And then the x values, 1, 2, and 3, are the 3 unknowns that we're trying to solve for. So we assume that we know all the a's and we know all 3 b's. And then we define a matrix problem, ax equals b, where x represents the unknowns. And we need to get a to the other side of that equation so we can solve for the x values. So that's an example of a problem where you use matrices. And A is not, that's going to be using the rules of linear algebra, not the rules of array mathematics. Here's another example where you might be wanting to do a multiplication of A times B. The A times B is perfectly fine. B times A is not allowed with this particular example. It would be an error if you try to do B times A. But if you do A times B, it's not an error. You can see in this graphic that what's going to happen is that the 3 A values across the top get multiplied by the 3 B values in the second one, and that top left value in the result is a single number, A11, B11, A12, B21, and A13, B31. Right here, that top left value is made up of 3 multiplications. Those 3 are added together, and it gets you 1 number. Then you've got to repeat that 7 more times. Every combination of the rows of A times the columns of B creates a number in this resultant array total of 8 numbers will be in that resultant. And after all that math, well, here's an example of it. You can see that there's the A is 12 numbers, multiplying by B, which is 6 numbers. The first 3 numbers in that, 1, 4, 3 times 5, 1, 2, gives this value, which happens to be 15. So the top left number is 15. You repeat that 5 more times and until you get, or a total of 7 times actually. So you get a total of 8 numbers in the resultant. Actually, I guess that's a total of 6 numbers. So in the resultant, so altogether 6 times you have to do that to get the, oh, I'm sorry, the example at the bottom only has 3 rows. So in the bottom example, you end up with 6 numbers, 15, 34, and so on. Go through that math yourself. Make sure you understand it if you're not already familiar with matrix mathematics. That's what MATLAB does by default. That, you might think that's a weird way to do math multiplication, but that's how matrices work. It's a very powerful tool in engineering, used in a lot of different areas. Most engineers learn it on their own, probably. There's some students do take a linear algebra class, but for the most part, you just kind of have to learn that on your own. And it's really not that hard. It's algebra. You just have to spend a little time with it. Now, on 2 square matrices, they must both be the same dimensions. If they're both square, the result is a matrix with the same dimension. In general, though, if you take 2 matrices, A times B, you would be able to do B times A if they're both square, but in general, matrices do not commute, meaning that the A times B in general is not equal to B times A. In fact, in the previous example that I did, only one of those was allowed. A times B was okay, but if you tried to do B times A, it doesn't work because the elements don't match up. Here's a couple arrays that are created randomly with the randi command. 3 by 3 matrix A, a 3 by 3 matrix B, and then multiplying A times B, you get one set of values. Multiplying B times A, you get a different set of values. Go through it, convince yourself that sure enough, those are the right answers, but they're not the same. That's what does not commute means. If it doesn't means that flipping them around, it's not the same answer anymore. Another neat, there's just a little off to the side idea that's pretty cool. It's something you can do in MATLAB is search with a relational expression all the way through and compare element by element 2 different arrays. In this example, I'm still continuing the previous example. Let me go back a page and show you. It's going to compare AB and BA, and if you compare, it turns out only one of the 9 numbers ended up being the same. Both, they have a 12 in the same spot. When you do AB equal BA, that's asking MATLAB to search and compare the 2 different arrays. AB is an array, BA is a different array. Compare them and see where they're equal. And you get a 1 or true only in the spot in the top right. You get zeros everywhere else, which means false. They're not equal except in the top right spot. So that's a neat little trick you can do. It's usually not just by itself. It's usually done as a bigger math operation of some kind. Allows you to quickly search through a couple sets of arrays and find the numbers you need, discarding all the others because the others will have a 0 there. If you then do a multiplication, you could use those zeros to weed out any numbers you don't want. The 1 in the right spot would keep the numbers you do want. That's just one of the neat tricks you can do with that double equal sign. Double equals rather than single equals. A double equals means are they equal? Single equals is just making them equal. All right, so when you have 2 vectors, vectors are lists. You can multiply vectors. However, they have to be the same number of numbers, and they can't both be rows. That wouldn't work. You do the row of the first times the columns of the second. So 2 ways that would work. The first one could be a row vector. The second one could be a column vector, or it could be reversed. The first one could be a column vector, and the other one could be a row vector. You do get completely different answers in that situation. If the row vector is on the left, the product will be a scalar. If the row vector is on the right, the product will be n by n, where n was the original number of numbers. It'll be a square matrix. So, for example, if H is 2, 4, 6, and V is -1, 0, 1. By the way, there's a single quote here after the definition of this second array. That's a shorthand for transpose, which means it turns it on its side. Rows become columns, columns become rows when you use transpose. So V is a column, -1, 0, 1. H is a row, 2, 4, 6. If I was to then do H times V, I get a single number 4. Double check, make sure that you agree with that. V times H, however, I don't get that. I get every combination of numbers I could imagine there. You end up with 9 different numbers when you do V times H. So very different. You don't even get the same size of array when you do that. Dot product is, or the dot command, dot A comma B, gets the inner product or dot product. A and B must be of the same size. Any combination of vertical or horizontal vectors, and in this case, the result is always a scalar, just like when you learn in physics about dot product, that's also called the scalar product. It results in a scalar, a single answer, not a vector. So for example, H and V, whether you do dot VH or dot HV, you get 4. It doesn't produce an entire 9 by 9 or 3 by 3 block of numbers. It doesn't produce 9 numbers when you switch them. All right, something called the identity matrix in matrix algebra or linear algebra. It's a square matrix with 1s on the main diagonal and 0s everywhere else. That's the main diagonal goes from the top left to the bottom right of the matrix. When you do matrix multiplication on any array or vector with the identity matrix, the array or vector is unchanged. It doesn't do anything when you multiply by it, which makes it equivalent to, it's the matrix equivalent of a 1. It's not a single 1 all by itself. It's a 1 on the diagonals and 0s everywhere else, but that's a occasionally useful matrix in matrix algebra. Since sometimes you need that identity matrix, there's a special function, EYE or I. You have to put in an integer in the argument of the function, IN. Will create an identity matrix, n by n identity matrix with 1s on the main diagonal, 0 everywhere else. When you start solving problems with matrices, sometimes you get into matrix inverse. One thing about matrix inverse, the definition of matrix inverse, in fact, is that when you take a matrix times its inverse, you get the identity matrix. Also, if you flip them and do the inverse times the matrix, you get the identity matrix. Whichever side you put the inverse on, if you get the identity matrix, then you found the inverse. So if B is the inverse of A, then not only is A times B equal to I, but B times A is I and A times B is I. And so as an example here, you can see that this 3 by 3 matrix, 2, 1, 4, and so on, if I right multiply it by its inverse, or if I left multiply it by its inverse, I get what's on the far right there, the identity matrix. You go through some of that, either try it out on MATLAB, that'd be the fast, easy way, or on your calculator. Your calculator will do these exact same computations. Try it out on MATLAB. Make sure that you do, in fact, get the identity matrix, regardless of which way you do that multiplication. There is a couple different ways to do inverse in your calculator or in MATLAB. On your calculator, a lot of scientific calculators will allow you to do the matrix to the -1 power. That's a very confusing thing because that's more like function inverse. Think of it more like function inverse. You know that the sine, for instance, the trigonometric function sine, you know that s psi n to the -1 power doesn't usually mean 1 divided by sine. It means the function inverse of sine. That to the -1 power with matrices is kind of like that. It doesn't mean 1 divided by A. There is no such thing as actual matrix division in linear algebra. It just doesn't. It's not a concept. A to the -1 means the matrix inverse of A. There's a couple other ways you can do it. You can do the INV function. It'll do the same thing. It finds the matrix inverse of A. There's a lot of different ways to do the same thing in MATLAB. MATLAB is smart enough to know that you can't just put a matrix in the denominator like that -1 power implies. It's smart enough to know that what you really want there is the matrix inverse. Here's an example where I've created a matrix A using the semicolon operator to do the row breaks. Then I find B with the inverse function. This is the same math we had before. Try this out in MATLAB. Then do A times B. Make sure you get the identity matrix. You'll also get the identity matrix if you flip it around and do B times A. There is a math tool sometimes that's nice to use called the determinant. A determinant is a way to look at a matrix and decide whether it has an inverse or not. If the determinant of a matrix is 0, then you could say the matrix is singular. It has no matrix inverse. It would be like you'd end up with division by 0 if you tried to find the inverse. DET or absolute value symbol will allow you to find the determinant of a matrix in math, but we just use DET in MATLAB. You don't really need determinant very often. It turns out it's computationally one of the hardest things to find. A determinant, finding determinants of big matrices actually is prone to a great deal of numerical error. It's kind of fun to play with determinants once you realize this, and if you want to start learning more about matrix algebra, you can create a matrix that is prone to a great deal of round-off error, so much round-off error that when you find the determinant, you might lose a lot of significant digits on the computation. So that's actually something to watch out for. MATLAB is pretty good at checking for stuff like that, but it is possible to do a really big determinant and have garbage come out of the determinant function. Anyway, so we try to avoid doing determinants. In fact, we try to avoid doing matrix inverse whenever we can. Both those computations are fairly slow when you're dealing with great big matrices. And there are times when engineers use software that has very large matrices, 1,000 unknowns, 1,000 equations, 1,000 unknowns. That's nothing for big structural models and such and so on. And so that's what this is all really about. Is a lot of this, at least, is handling big matrices. Compute the determinant with DET. To have an inverse, for a matrix to have an inverse, make sure that it's square. It won't invert if it's not an n by n matrix, and the determinant must be non-zero. People will talk about matrix division, but really that's just using the division sign on either side of the matrix. Left division, there's a left division sign, like a backslash. There's a right division sign. They do things in MATLAB with matrices, but they're not really what you might think of as matrix division. There's array division, two kinds of array division. If you are trying to solve the equation AX equals B, then a fast way to do it, a cool way to do it, is down here at the bottom. X equals A, and it's kind of like you're sliding A underneath B. A, put it underneath B. Think of it that way. What you're really telling MATLAB to do is use whatever tricks it knows to solve the problem AX equals B, and do it without taking an inverse. That particular method of doing it is preferred. This other way will also work. You could find the inverse of A, then multiply it by B. That also works with small matrices. It's perfectly fine. But if you have very large matrices, like I said, 1,000 equations and 1,000 unknowns, then you need to start using a trick like this, which is actually better able to handle the big matrices and the sorts of numerical problems that come along with those. Yeah, here's that suggestion again. Use A backslash B if you want to solve the problem AX equals B rather than this other way. I don't really care which way you do it. I'm not going to give you a giant matrix to deal with, but just keep in mind there is a right way and a wrong way to work with matrices generally. 2 to 3 times faster. It really depends on the size of the matrix. As the matrices get bigger, then it can be much faster doing it the first way and less error. Then you could also think of right division. That's kind of a funnier thing. It's pretty unusual to be looking at this bit of math, x times c equals d, where you're trying to solve for x. Notice how the array c is on the right-hand side instead of being on the left-hand side. And that's a big deal since matrices don't commute. You would need to right multiply by c inverse to get to the other side. So the solution to this problem is x equals d times c inverse rather than c inverse times d. To do that, d divided by c is what you would use. But this isn't interchangeable with the other one. This way only works when you're solving this less common problem of x times c equals d. Most of the time you'll do it the way I said on the previous slide, left division rather than right division. Or just use the INV command if you want to ignore my warning about which way is faster and better. Another way of saying element-wise operations is element-by-element operations. Addition and subtraction of arrays is always element-wise. Doesn't matter whether you're doing arrays or regular matrix mathematics. But it is possible to override matrix math and do array math with multiplication, division, and exponentiation. By default, MATLAB does everything as if it was doing linear algebra, as if it was using matrices. But sometimes that's inconvenient. For example, if you had a table of numbers that all had lengths of rectangles and another table of numbers that all had the widths of those same rectangles, and you wanted to do length times width equals area, and you wanted to multiply it item by item, that's an example where you don't want to do matrix math. You don't want to do row times column and add those row times column products up. You want to just multiply the corresponding elements of two arrays. And so you can do that. Again, though, if you're going to mix those things together, a times b, or a divided by b, or a to a power, a to the b power, if you're going to do those kind of things, then they do have to be the same size and shape. To do that, it's a simple trick. Just put a dot in front of the operator. You're going to suppress the matrix mathematics and revert to element-by-element mathematics. So that's a period in front of the star. In other words, it would be a dot star b. So you have a star b normally, but between the a and the star, you're going to put a period sign. Same goes for exponentiation or left and right division. You can override the regular mathematics, and that's the default in MATLAB, and instead just do it item by item. Here's a simple example of that. If I have A is 4 numbers and B is 4 numbers, and I want to actually multiply them together and get the answer A1, B1, A2, B2, and so on. If this is what I want, the more simple result, you might say, then I have to put a dot in front of the star. Same thing with division or exponentiation. All of these are perfectly fine in terms of array mathematics. If you're doing linear algebra and dealing with systems of equations, you probably would never do this. But there are other situations where this is a really handy thing. So you have to suppress the normal behavior of MATLAB with the period in front of whatever math operator you're using. Same thing here. It works not just with vectors. It can be done with arrays. If you have 9 numbers in A, 9 in B, and you want to, this is like my length. If A, let's imagine A is a bunch of lengths, B is a bunch of widths, and I want to do length times width to get a bunch of areas, that's what would happen if I put the dot in front of the star. It would suppress the regular matrix math and instead just multiply item by item. Same thing with division or exponentiation. And then here's an example of that. If I had A is 1, 2, 3, 4, that's 2 by 2 matrix. B is also 2 by 2, and I do A dot star B, I get 1 times 0, 2 times a half, 3 times 1, and 4 times negative a half. Gives me these 4 numbers in C. That's a lot simpler than if you did if you left off the star. You'd get if you left off the dot. If you left off the dot, then it would be doing row times column. It would still work. It would just give totally different answers. Now, if the matrix dimensions do not agree and you try to do any kind of operation where they don't agree, you'll get this message: matrix dimensions must agree. So if I try to do A times B using the dot star, that's not going to work at all. The only way I can do A times B is if there's the same number of numbers, same shape in both. So because A is a 2 by 2 and B is just a column, I could do A star B, but I can't do A dot star B. That'll be an illegal operation. It says matrix dimensions must agree. But A star B gives me 2 numbers, and you can check to make sure that's what the rules of linear algebra say it should be. It is possible when you're dealing with square matrices that you accidentally forget the dot when you should have had it, or you put in a dot when you shouldn't have. You really need to pay attention in MATLAB to this particular aspect. Some matrices, both operations work. A times B works. A with just the star. A dot star B also works, but they give completely different answers, and they're physically very different situations when you would use them in engineering. You need to make sure you pay close attention to which one you're dealing with. And so here's an example of that. Two 2x2s. I can do A dot star B. I get one answer. I do A star B. Totally different answer. And you need to know which one is the correct one for the situation that you happen to be in at that moment. Sometimes you want to calculate the value of a function at many values of its argument. This is a neat little trick for a polynomial. If I had x as a list of numbers, I created this list using the colon operator. That's a colon, 1 colon 8. X has values 1 through 8. I did not put a step size in there. When you leave off the step size is 1. So it counted by ones from 1 to 8. And then when I put it into this expression, it works fine, but only if I put the dot in front of the exponent. By putting the dot in front of the exponent operator, x dot caret 2, it's going to square all the x values, the individual x values. Then it's also going to multiply all the individual x values by 4. It's going to subtract 4x from all the squares of the x values, and it comes up with this list of numbers, this list of y values. If you're trying to create a polynomial from a list of x values, that's one way to do it. There's also a polyval function that will do something similar, but this function, or this method of doing it, is a quick and easy way. But if you try doing it with without the dot, you'll see you get an error. You can't square a vector. The squaring operator only works with a square array. Many functions will take entire arrays as inputs also. So when input is an array, the output is an array of the same size, with each element being the result of the function applying to the corresponding element. So what that means is, if I take an array and I throw it into the sine function like I'm doing here, or the cosine function, it's smart enough to know to do cosine on each one of those inside there. There's no special matrix mathematics there. It's not doing any rules of linear algebra, but it is creating a loop for you. If you take a bunch of x values, put it into a trig function, it will automatically run through a loop and use that trig function on every one of the elements in either your vector or your array. I'm showing it here with a vector, but it also works with a table of numbers. It'll just do the sine of every number or the cosine of every number or whatever. It's really quick and convenient, no loops needed. And a lot of the functions work this way, also the math functions, and then there's other functions that are specifically designed to deal with vectors or arrays. Mean finds the average, max finds the maximum in the array. It also it can return the location if you want. Max and min, if you do the help command on those, just type help max or help min at the command line, you'll see that they have different ways you can set up their outputs. And one of the options is that it'll show you not just the value of the maximum, it can show you the index location of the maximum. Sum adds it all up, sum adds the vector, or if it's a table of numbers, I believe sum will just add up all the columns by default. Or if you choose to do it differently, it can add up all the rows. You can sort a vector in ascending order. Here's more functions that are pretty cool you can play with and read about, use the help command. Just by typing help median, for instance, it'll pop up a little description of that function and a little example usually of how it works. Vector cross product, determinant, inverse. So those are examples of functions. There's many, many functions in MATLAB for working with vectors and arrays, and those are some examples. One last little topic, random numbers. You might think that's in there mostly for things like games or whatever, but actually random numbers are put in there, or pseudo-random numbers, because engineers and scientists use them a lot in things like simulating noise, testing their control systems and how they respond to noise, using them for search algorithms to try to converge on a solution to a tough math problem. That's called a Monte Carlo search, where you guess a huge number of guesses, and the ones that seem to be kind of close to the right answer, you then follow on those with more sophisticated algorithms. But you start off with the massive random search to narrow down the field a little bit. Computers are so fast that kind of an approach actually is very effective in the initial searching for solutions to tough mathematics problems and engineering problems. So there's a lot of reasons why random numbers are needed in engineering, or pseudo-random numbers. Now there's three commands, built-in commands for doing this: rand, randend, and randi. You can create scalars, vectorces, or matrices of random numbers. Here's an example of doing that to create a list of numbers using the rand command. You can see it produces 10 random numbers and ranging in various values from -5 to 10. And so there's a little formula. The key right there is the rand command. That creates a vector, and then every element of that vector is multiplied by 15. Then every element in that resulting vector has 5 subtracted 5 from it. So that's an example of how to create a list of random numbers, a flat list. It's not going to, by default, be a bell curve or anything like that. It's flat, meaning that every number in that list was equally probable. When you start doing statistics, statistics is a huge issue with engineering, and why we have another good reason to use random numbers. Statistics can be a very easy thing if you just throw a lot of random numbers at it and you count what comes out. But if you're going to do that, you got to know the type of noise or the type of random numbers you're sending at it. And flat is the most simple thing, where you create you have a range of numbers, and every number in that range is equally probable. But a lot of things go on a bell curve, and so that's a different type of noise or random numbers that you'd have to work a little harder to generate. Here's another example, generating, again, uniformly distributed random integers between 50 and 90 using the randi command. There's different ways to use functions. Functions in MATLAB have different variants, so if you do help, R-A-N-D-I, 2 words, help, R-A-N-D-I, you can read about the different ways to put in the commands to get a list like this, random set of numbers. Now, randn, this is what I was talking about a second ago. It actually creates a normal distribution, which is your classic bell curve. Between 0 and 1, mean of 0, standard deviation of 1. So the average is 0. It spreads out from 0 randomly, and that might seem kind of limited, but then you can do the same thing I was doing on the other examples there. Multiply by a number, add a number. That means you can move the average, you can change the standard deviation, and that can be very useful in different kinds of problems. Here's the way you would do it. Using that rand function times this standard deviation that you want plus the mean that you want. With that method, then you can get any bell curve that you need to simulate noise or whatever. Then you can also round that. The round command rounds to the nearest integer. So if for whatever reason you only are having integers coming out of your random process, like let's say you were dealing with estimating number of errors, if you're looking at defective products coming off of a manufacturing line, it's a very common statistics problem that engineers have to face. How many flaws do we expect? How many defective parts should we expect based on our random sampling, that sort of thing? And that would be an integer. The number of defective parts is an integer. So you'd be rounding that noise or that bell curve in that case. And that's it for this section. If you have any questions, please get in touch. Thank you.